Thank you, Alex. Not laughing at you guys. Thank you, bigly. Okay. Household electricity. What's the voltage in your walls? 120. Yeah, good. But voltage, as it turns out, we'll see in a few minutes, is really not nearly as important as, well, you'll see. Forced to solve your homework problems, I'm going to introduce something practical to solve your homework problems and know what the heck the labels at Home Depot mean, or the Maytag store. Do they even have Maytag stores? They don't, do they? To know what the labels on appliances are telling you, I need to teach you a new unit, which is just a synonym for joules. Watts power again? Yes, but the definitional equation is energy per time, energy per second. Okay, what happens if I multiply watts by time? What do I get? Watts, joules per second times seconds is joules. What's joules? No, watts is power. Watts power. Joules are energy, right? Okay, so energy, instead of being measured in joules like they should, appliance manufacturers measure them in kilowatt hours. If you pay an electricity bill, APS or SRP or whatever bills you in terms of kilowatt hours, dollars per kilowatt hour. Your electricity bill, take a look next time, you'll see. That's the unit. You can convert that to dollars per joule. That's a very small number. A joule is a relatively small quantity of energy. Okay, anyway. 1 kilowatt hour is 3.6 million joules. Or shall I say million joules? Write that down. You need that. We're going to convert in a second. 3.6 million. Let's actually practice. The 3 o'clock class had some trouble with converting seconds to hours and months and stuff. Let's practice a unit conversion real fast. Why is kilowatts times hours 3.6 million joules? Work it out. Work it out. Like a constipated mathematician, work it out with a pencil. Okay. What's a kilowatt? 1 kilowatt times 1 hour. Note, not kilowatts per hour. Kilowatts per hour. Watts divided by time is something I don't know. Kilowatts times hour. What's a kilowatt? Convert kilowatts to watts. How many watts per kilowatt? Yeah. And if I wanted to express this as a unit conversion, I like writing out as a fraction. I'm going to multiply by something which kills kilowatts, which kilowatts, which kills kilowatts and converts to watts. I am multiplying by the number 1 and the units which cancel out. So now I need to think, how many watts in a kilowatt? How many kilowatts in a watt? Which one is the 1,000 and which one is the 1? Is a watt bigger or is a kilowatt bigger? Kilowatt is a bigger unit. So should we have 1,000 watts equals 1 kilowatt? 1 kilowatt is a bigger amount of electricity. 1,000 of the little things equals the big things. Okay, and algebraically, if I have kilowatts, and then I multiply that by something, a fraction with kilowatts downstairs, kilowatts cancels. Units behave like algebraic. Units behave like algebraic. Oh, for dog's sake, what I'm trying to say is units behave like algebraic terms. You can cancel a unit on top with a unit on bottom. Okay, what's an hour? In SI units, I would convert, did you say 60 seconds? 60 minutes. I would convert hours to PBS shows, no, to units of time, by saying I want hours downstairs so they kill the upstairs units. And I know hours per minute, 60 hours per minute, right? 60 hours is a minute? Maybe it feels like it, 1 minute of physics class feels like 60 hours. No, 60 minutes is 1 hour. Think of it carefully. Don't get these confused. Go get it backwards or you screw everything up forever. Hours cancels hours. And then when I want to get to SI units, I don't want minutes, I want seconds. How many seconds in a minute? 60 seconds is 1 minute. So I am not changing the number. I'm multiplying by something which is 1 over 1, which is equal to 1. 60 seconds is equal to 1 minute. So I'm not changing the meaning. I'm just changing the unit. So what have I got now? Watts times seconds. Watts a watt. It's a joule per second. Yes? Right? Look, I've got watts times seconds equals joules. 1 times 1,000 times 60 times 60 joules. 1 kilowatt hour is equal to 1,000 times 60 times 60, which is, if I do my math correctly, 3.6 million joules. Oh, that's what I said before. Are you okay with this process of unit conversion? For real? No, I never get good questions that way. Turn to your neighbor and talk through what Tucker just did and why he did it. And then Tucker will ask you for a question. Okay, ask me a question. I mean, ask Tucker a question. Tucker wishes for your questions. You really comfortable with unit conversions? We're going to do a couple today. Okay, well, I don't see anything. Moving on. These numbers are wrongo bongo. They were named in 2000. I made these slides originally in 2022. As everyone knows, the last 3 years have had a little bit of inflation. I don't know the current. My wife pays the electricity bill. I don't know the current rate, but I guess it's bigger. I apologize for making you feel bad about how bad your electricity bills are now. Anyway, work it out. Work it out with a pencil. Question A in the Google form. Oh my God, correct answers. I just love it when people are right. Whole gold doubloons. Do I even need to look at the names to know who asked that? You should check. These numbers are old, but they are actually sort of order of magnitude. Do you really spend more than $1,000 on electricity? Check your numbers. Did you know that the phrase pieces of 8 refers to the fact that you used to cut Spanish doubloons up into 8 pieces? They used to have marks on it so you could cut them up. Pieces of 8 referred to the Spanish dollar, which was used as currency in the Americas for a long time. The 8 slices that you could conveniently easily cut a, I don't know if it's a doubloon, up into. So pieces of eight is referring to money. Because you could cut the coin up and it'd be worth 1/12. Huh? Pirate movies, right? Pieces of eight, says the parrot. Really? Oh, there's your homework. Forget mastering physics. Go watch Long John Silver. Muhal. Okay, great. 12 amps. What you smoking, fool? Dollar. Dollars. Okay. As the vast majority of you correctly reasoned, kilowatt hours per dollar, dollars per kilowatt hours times kilowatt hours equals dollars. Yeah? 129 doubloons. Also, did you know that the word dollar refers to Talher, the German word for a region in Germany where an early mint was? So we stole the word dollar from the German region. Very important knowledge. Now I ask you a trickier question. If you know that there is 1,000 kilowatt hours, what's the voltage? House voltage? 120 volts. And if you know those definitions I reviewed, P equals IV, power is energy divided by time. V equals IR. No, you don't need V equals IR. If you know those two equations, solve for this. What current do you draw on average? It goes up and down depending on air conditioning and stuff, but what current did you use this month on average? Just like the farmer, I want you to work with each other. I'm on fire today. God, I'm funny. What equations did you say again? Well, what equations might we use? If I'm talking about energy and I'm talking about current, how does energy and current relate? Energy is power per time. I'm talking about a month, hey, a month, that's specifying a unit of time. You find the average power being used? P equals IV. Huh. 12 cents for off-peak, 33 cents for on-peak. Thank you, Melanie. I'm curious. House wiring melts at about 20 amps. If you got 120,000 amps, check your math. Average current would be already, you know, amps, not amps per day, just amps. Amps charges per second. I mean, another way you could do this is find the total charge transferred. You've got energy. You could find time. You got voltage. Use those equations. Chug, chug, chug. Chong, chong, chong. Look. What does kilowatt hours tell you? Energy. You know PIV. You know power is energy divided by time. Yeah. I tell you in 1 month, that's the unit of time. Tell you energy, time, and you know V, voltage is 120. Solve it. You can do this. Yeah, 29, 30, 31, I don't know, it rounds. 1 month, 1,000 kilowatt hours. How many sig figs there? Okay, I'm asking for current. Current is not measured in kilowatt hours. And sanity check, tens of thousands of amps should alarm you. You have not converted units to SI units before multiplication or division. Don't look unless you want a hint. Okay, hint time, hintification, hint. Hint is on the board. Only like 3 people have the answer right now. Remember, if you want SI units out of a calculation, put SI units in. Power equals the energy divided by time. You can't use joules and hours. Joules per hour. No, you want watts as joules per second. Convert to SI. You got all the conversion constants or can figure them out. You can do this. But don't just plug in energy in kilowatt hours and time in months and volts and volts. E over V is a true equation. Give me a number. One, two, three, four, five, six, seven, eight, niner, diez, doce, trece. 13 correct answers out of 60 people in here. We could do better than that. Okay, follow-up questions. I want to see where you're goofing. Show me your goofing goofs. Show me where you're goofing. What is that? That was question A, right? Right. No, that was question B. Okay. Work up to it. Can you tell me the energy in SI units? Can you tell me the time in SI units? Can you tell me the voltage in SI units? When it gets E wrong, gets bopped with a bopping stick. I am confused on how to find the voltage. Ask your neighbor. The voltage in a house is a number y'all should know. How would I get the volt? Ask your neighbor. We already talked about the voltage in a house. I'm not sure how to get the volt. Ask your neighbor. Energy is not measured in watts, yo. Energy in SI units. Tell me the energy in SI units, in our standard physics units, peeps. The only thing you don't, that is crucial to know that you haven't seen, kilowatt hour measures energy, kWh measures energy, and it is equivalent to 3.6 million joules. That's the only thing that you need. 3.6 million joules, 1 kWh. See if you can reason through the questions on the board. And I've got 13 correct answers for part six, part C. 14, 15, 16. There's still 3 quarters if you're not converting. Okay, I've got someone telling me the units of energy, time, and voltage. I'm asking for numbers for CDE and then going back and fixing B. Okay. My friends, we did a unit conversion example. I begged y'all to tell me if you were struggling here. Let's convert kilowatt hours, 1,000 kilowatt hours into into joules. What did I tell you? There are 1,000 kWh, kilowatt hours, and then we convert this to what unit? The SI unit is the joule. So I can multiply this by how many joules there are in each 1 kWh. What number did I tell you to write down? 3.6 million. Kilowatt hours cancels kilowatt hours. The answer is not 1 million joules. The answer is not 0.1 joules. If I multiply 1,000 by 3.6 million, yeah, 1 kWh equals this many joules. 1,000 kilowatt hours equals 1,000 times that many joules. Please use this process to tell me how many seconds 1 month is. And don't Google it. If I want time, telling you energy divided by time times volts, I want time in seconds. What time? 1 month. Household voltage is not 11. Please ask your neighbor. Household voltage is not 139. Ask your neighbor. I'm asking question C. Tell me energy in SI. Tell me D is the time. Question E is the voltage. And go back and fix your answers for B correct. I mean, the question, you're using 1,000 kilowatt hours in 1 month. 1 month is the time, but 1 month is not an SI unit. Hours and days are not SI units. Please convert to seconds. Give me the seconds. Oh God, it's recording. Again, if you are writing 1,000,000 watts, please review my answer in question C. The answer is not 1,000,000. Okay, question E. If you don't know this, write this down. What we said at the very beginning of last lecture, and what many people have seen on the side of appliances, plug this into house voltage is 120 volts. Know that. I will assume that you know that house voltage is 120 volts on everything. Bang, bang. Now time, let us convert 1 month into seconds. What am I going to multiply months by? I don't know how many seconds in 1 month. I do know how many days are in 1 month. So am I going to multiply by 30 days over 1 month? Am I going to multiply by 30 months over 1 day? Am I going to multiply 1 day over 30 months? What is the fraction I should use to convert months to days? What goes upstairs? What goes downstairs? Days go upstairs, months go downstairs. I wish to kill months. Die! So I need to have a fraction with months downstairs. I write this out as how many mon, how many day. Now, reason, check, think. Is it 30 days in a month or 30 months takes 1 day? Last I check, the days is 30, the months is 1. Bang, bang. If I multiply 1 month times 30 days per month, I get that the time I'm talking about is 30 days. Yes, well, that should make some kind of sense. How do I kill days? I don't know how many seconds are in 1 day. Well, actually, I do, but you don't. But many people, most people don't have this memorized. So I want to kill day. If I've got days upstairs, I want days downstairs. What do I know about days? There are 24 hours in a day. 24 hours equals 1 day. Bang, bang, days are gone. What about hours? I don't know about hours. Well, I do know one thing about hours. 1 hour is 60 minutes. Hours goes downstairs because I want to kill him. 1 hour, 60 minutes. Bang, bang. 60 minutes? 60 minutes, how long's a minute? 1 minute is, last I checked, 60 secs. 30 times 24 times 60 times 60 is 2.6 million. Okay, 75% of the class missing this is a problem. I thought your chemistry classes have unit conversions all over the place. Please turn to your neighbor and review the process that we've been doing. You need to be able to convert units. I assume that you have done this in your other classes. And I have just walked through 4 times how to do this. You must learn this fast. Please review and then ask me a question where you're confused. Ryan, you tell me, does it change the number? Ryan asks, can you use 31 instead of 30? 31 equals 30 to this degree of precision. You mean at the end of the month? Hey. Oh my God, look at all those correct answers in B now. That's more like it. What? Do not want. What the what? What are you smoking? Thank you, Windows. Okay, give me a question. Where is unit conversion killing you? No, you don't have to admit to not knowing. You just talk to your neighbor. Tell me where your neighbor's confused. You love your neighbor. Won't you be my neighbor? To summarize, unit conversion is this deep. Here's how to do it. You write down the number you want to convert. You multiply by a whole bunch of equivalencies. If you're trying to kill a unit that's in the upstairs, the equivalency had better have that unit in the downstairs. If you wanted to convert kilometers per hour into kilometers per second, you'd want hours upstairs to kill the hours downstairs if you got that fraction. You don't have to know how many, kilometers there are in a mile. If you know how many meters there are in a kilometer, how many centimeters there are in a meter, how many centimeters there are in an inch, how many inches there are in a foot, and how many feet there are in a mile, you can figure it out. Don't Google this stuff. Practice it. If you're screwing this up, practice this unit conversion. Because there are 1,000 things in physics that have 1,000 steps, that have deep conceptual challenge. This can be easy peasy. Last chance for questions? And the other thing that at least wrecked the 3 o'clock class is knowing that power is energy divided by time, current is power divided by voltage, and that you can plug equations into each other. Please, 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 if I ask you about quantities that are related to each other, look at the core ideas in here. What's an energy? What's a time? What's a current? How can we stitch these equations together? Use your core equations and you can find things that I haven't explicitly told you, follow these steps. You could go from one to the next to the next to the next. By the way, there's more than one way to do this. Last chance for questions about this? Yes, no, maybe so. Final answer, 12 amps. As a whole bunch of people got correct after walking through the conversions. Okay, okay. We haven't practiced a bunch of unit conversions. I think I'll start putting these on quizzes and tests to force you to, though. There's no depth here. You can do this. Everyone can do this. Okay. Moving on. That is not, unit conversions is not the big point of today. Let's talk about how to kill someone. Biological effects of electricity and electrical safety. Some fun concepts. Here are a couple numbers. Write these down. This is supposed to be an approximately equal to rendered incorrectly. Okay, so there are dose two factors for how to kill someone, for danger of electricity. One is current, not voltage. Two is path, where the current flows. You need these numbers to answer questions and do things. These are rough estimates, by the way. It varies from person to person, to condition, whatever. Oh, also, notice DC and AC are different. They pass through your body in different ways. We've got different numbers for these. How hard is it to feel a current? Your body, your nervous system registers ouch, or not even ouch, but tingle at something like the 3 milliamps DC, 1 milliamp AC level. You are barely able, not ouch, you are barely able to feel it. Oh, there's a tingle at that level. Look, it only takes 15 times as much to kill you. Stop you from breathing if it passes through the wrong place. 15 milliamps of alternating current. 15 milliamps. 0.015 amps. Compare that to these projectors are probably drawing, I don't know, 10 amps. 10 amps. 1,000-ish times as much current as is needed to kill you just to run a projector. This room is, I don't know what the current draw of this room is, 100 amps or more. Whoa, electricity is deadly all around you. If even a tiny fraction of that passes through your body, you dead, boy. Okay, do you guys know what fibrillate means, by the way? What's a fibrillation? It is not the same thing as stopping your heart. If your heart stops, it'll restart itself usually. An AED, an automatic electronic defibrillator, intentionally stops the heart and your heart restarts itself. Fibrillation means your heart is confused, the pump is not working, your heart is quivering. So, by the way, don't tell me how hard it is to stop your heart. Tell me how hard it is to fibrillate your heart. That's the dangerous thing. Confusing the internal timing circuitry, biological timing circuitry. Okay, and how hard is that? 500 to 1,000, 500 DC, 100 milliamps AC. Incidentally, higher currents, an amp flowing through the wrong place might be ignored by your body. Don't test this. I've been told that higher currents might not actually confuse your heart, stop your breathing necessarily, make it so you can't let go. People survive lightning strikes of, I don't remember this number. It's hundreds to thousands of amps, I'm sure. People can survive that. Interesting fun fact, if you play with high voltage electronics like I sometimes do, high voltage vacuum tubes, yeah, retro for the win. High voltages, there are a couple of rules of thumb, a couple of rules of heart that we learn if we wish to survive, is high voltages, thou shalt always work on energized circuits with one hand in thine pocket, because the path, as I'm about to show you, fingertip to fingertip passes through the heart, electrical shock passes through the heart, that way you die. If you are working one-handed, the bad path of electricity, finger to pinky to thumb, oh, you just lost a hand instead of you had died. Other rule, interesting rule, thing that you might wish to know about is if you get a large-scale shock of lots of amps, like maybe from a high voltage, high current power supply, this is kind of morbid. Plug your ears if you're easily grossed out. Yeah. High current will not necessarily stop your heart, stop your brain, stop your breathing. It may hold your hand so you can't let go. And then the cause of death for very high current shocks is being baked alive, broiled alive from the inside, which takes a long time and is very painful to be burned alive from the inside. and you smell meat cooking because you are meat and you are cooking. So the rule of electricity for that is thou shalt never work on high current, high voltage electronics alone. Thou shalt always have somebody that can smack thee with a baseball bat to get you away from the conductor and then call the hospital. So don't work with two hands and don't work alone. Just love the thought of broiling alive from the inside. Okay. Oh, also, fun facts, fun facts. Did you know that electricity doesn't stop you from letting go? It's not an electrical force. Electrical force of a current is very, very small. It is your own muscles being contracted by the current flowing through them that makes it so you can't let go of a current. That's a real effect. You get zapped through the muscles, your muscles contract, oh, you can't let go. If you don't hold on to the wire, you may, it is not movie BS. So many pieces of physics are movie BS. You are not thrown across a room, or you are thrown across a room. That is a possibility. If you're not stuck holding on to a conductor, you can be thrown across the room. It is not the electricity that flows you across the room. It is your own muscles contracting your legs or jerking your muscles. It is your own body that is throwing yourself across the room. Okay. Anyway, some fun facts to know about death. Let's move on. Let's apply this. As I just said, thou shalt work on powered circuits with one hand in thine pocket, lest thou wish to loseth thine life. Path is vital. Passing finger to thumb, you lose a hand. Passing from one hand to the other hand, you lose your heart. Oh, I know which of these is more important. Well, for me, it's fingertip to fingertip because then I can't type. I lost my heart when I became a professor, of course. Now, we just talked about currents. To understand the danger of 120 volts AC or whatever, or any voltage, we need to know resistances. Do you remember the equation V equals IR? You better. We're going to introduce a model of resistances. And there's not just one resistance for your body. I'm talking about path here, so I'm going to tell you about the resistances of different body parts. No, not that body part, you pervert. Here's our model. Here is you. Here is your body. Here is your body not on drugs. You can measure this, by the way. You can measure some of this with an ohm meter. You just go to the lab, turn your ohm meter onto the highest setting, touch both electrodes. No, that won't kill you. Ohm meters are safe. Measure the resistance fingertip to fingertip. It's about 2 million ohms, depending on how sweaty you are. What you're measuring is about 2 million ohms, is the resistance to hop through your fat skin. Your skin has fat in it, duh. Very low conductivity. Hop from fat to warm, squishy, conductive liquid insides over to the other finger, hop back out, and that's about 2 million ohms. Your skin layer is something on the order of a mega ohm. Okay, so every time you pass through the skin, it's like 1 million ohms to get to where conduction is easy. That's less if you're sweaty, by the way, then current flows along the surface, whatever. Your arm, much smaller inside, 310 ohms. Your torso, write these numbers down, by the way. Torso, 30 ohms, either arm to arm or arm to leg, or I guess leg to leg, I don't know. Leg to leg should be smaller. Ouch, by the way. Other arm, 310 ohms. Legs, 290 ohms-ish per leg. So with this model, which I will ask you about on the quiz, I think, on the homework definitely, we can calculate just how much current you're going to pass through your kidney, through your heart, through your groin, I don't know. I forget what the homework question says. And to do this, find the total or resistance. I will provide you the voltage. You calculate current. Good? How do I calculate the resistance if I've got this resistor in series with this resistor in series with this resistor, blah, 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 blah? Series, that's the series addition formula. Add them straight, yeah? 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 Okay. So, arm to arm to leg, or leg to leg. Oh, it is leg to leg. We're going to say that passing through the torso, any path that passes through the torso is something like 30 ohms. Whenever current enters or leaves the body, we add the skin resistance, which is the resistance to go from the outside to the inside. That's about a mega ohm. If I recall correctly, this 10 kilo ohms is to travel along the skin. Whatever. I'm not going to ask you the 10 kilo ohms. We're going to use a mega ohm for that. No, we're not. This person must be thin-skinned, if I'm thinking about this correctly. Whatever. Oh, right. Hold on one freaking second. Go back a slide. Sorry, I forgot to say this before. Paralyze your breathing, fibrillate your heart, stop your muscles from contracting. Your nervous system detecting RMS or peak. What do you think? Peak. What about if I gave you a problem with baking alive from the inside? Do you care about average or peak power? Average. So I'd use RMS if we're talking about boiling you. We'd use peak voltages to say, is that going to stop your heart? Is that going to confuse, not stop. Is that going to confuse your heart? You only need to pass those charges in for an instant. I would care about peaks. Does that make sense? I can give you an RMS voltage. Thou shalt convert to RMS current, peak current, before you answer the question. Did everyone get this model written down and the thresholds written down? Great. Let's do a problem. What letter are we freaking on? I forget. Also, I don't know my alphabet. Where are we? G? F? What the F? Here we go. What is F? How can skin resistance be so small? .707. 0.707 turns peak into RMS. Huh. So it really is to pass through the layer if you're sweaty. Fascinating. I didn't know that. So the 2200 is maybe they used lotion. It put the lotion on its skin and it gets the current again. I didn't do it. What? What? Must moisturize the skin, decrease skin resistance, and allow decrease the resistance, allow bigger current. Huh? Yeah, if you're passing a given current through, if there's less resistance there, there's less power dissipated in the skin. If there's not catching on fire from the skin. Huh. Delicious. Oof. So morbid. I think I heard that. But why would it, isn't current still going up if you're dropping this big factor, the skin resistance? I think there's something that I don't know here. Good question. What? What do you what? Tell me well, Tell me the amps and then tell me what is that dangerous? What kind of death or not is this going to produce? How is it going to kill you? What would shoes do? Is it? Oh. Or is it emergency? Hold on. Hold on. Hold on. Hold on. You're right. You're right. Automated external defibrillator. Huh. Huh. Biphasic. Huh. Monophasic zap once, biphasic zap twice? Triphasic zap thrice? Phasic. How many pads did a biphasic have? How many pads does a different one? Okay. Now I'm curious. What's it called? Yeah. Biphasic what? Biphasic versus monophasic defibrillator. In two directions versus one direction. So it's an alternating current, sort of. Oh, it's not a sine wave either. Interesting. There must be some really interesting biophysics inside this. Biphasic waveform. Fascinating. Yes, it is very dangerous. Tell me the current and how is it going to kill you? OSHA violation. Yes. Not stopping the heart, fibrillating. He, what's this he? Don't gender them. Okay. A couple of people are confused how to start. What kills you? Amps or volts? Amps. So if I ask how dangerous is it, you need amps. What did I tell you in the problem right here? Volts and stuff about ohms. That's what the previous slide was. How are volts, amps, and ohms connected? Oh, I haven't burned this into your brains yet. Ver, baby, ver. If you know B and you know R, you can find I. What's R? Look at the previous model and use the series addition formula to find the total resistance. Yeah. Yeah, what? And at the end of the day, you say you got the RMS voltage, it gives you the RMS current. If we care about well, calculate the magnitude. If we're at the baking alive or broiling alive stage, then you care about RMS. If you want to know whether it fibrillates the heart, convert to peak, I think. There is no thing as RMS resistance. Resistance doesn't alternate. There's no DC versus AC. Plus the skin resistance twice to get into and out of the squishy insides, the delicious organs.
Oh my God.
No, look at the previous slide. Whenever the current enters or leaves, add the resistance. Once in, once out. They're 310, right? 310, 310, 310, 310.
Oh my God.
Okay, here's how I find current. Find R. R. Pirate's favorite physics variable. You're going into skin, through the arm, through the torso, through the other arm, out the skin. 50-50. Yeah, once in, once out. Voltage I gave you, the change in voltage from a 480 line to a ground. Remember, just voltage doesn't cause a current. Change in voltage. One has to be touching 0 volts. 480 volts change, that's RMS. I is V over R. I got 0.095 amps. We're not talking about broiling, baking, boiling inside. We're talking about organ, heart, whatever stoppage. So I convert from RMS to peak, divide by 0.707. Remember, RMS is 0.707 peak. So peak is RMS divided by 0.707. 0.134 amps, or I was talking about milliamps earlier. Convert to milli, 134 millis. All right, what does 134 do? 134 milliamps. I look back at my chart. What's 134 milliamps? Oh, fibrillation. Danger, danger, danger. Question me. Thank you. That was a test, and you passed. Yeah, yeah, exactly. So where's the path if I'm working with my hand and right? The electricity flows from high voltage to low voltage if I'm brushing against something like that. Yeah, absolutely. There's no path, there's no 0 volts on my other side. Unless I'm standing in a bathtub. If I'm standing in a bathtub, right? I do most of my electronics work naked in a bathtub, of course. You know, touch a toaster coil while there's a bath running, right. Then there's a path from your foot to ground, and you're touching 120 volts 169 volts peak on this side, then you would then you would then you would die. It doesn't matter if you're in your bathtub clothes or bathtub naked, you're still gonna die. Okay. Questions, other people's good questions about this. Okay, this royally screwed over my 3 o'clock class. Read the question. Let me give a hint. It's not 120 volts on high voltage transmission lines. They have tens of thousands, hundreds of thousands of volts on high voltage transmission lines. Do not assume that you are getting a 120 volt shock. Reason through this with me for a second. 7 ohms is the total resistance for 100 kilometers of line. Those are big fat conductors in the high voltage transmission lines, okay? They're really trying to minimize. 200 amps flows through 7 ohms. Okay, how much of that 7 volts do you get if you're holding like this 15 centimeters apart? What fraction of 7 ohms is from here to here in the transmission line? What fraction of that? Well, methinks 15 centimeters divided by 100 kilometers is the appropriate fraction to use. Yes? If you know the resistance of this length, then the resistance of this length is the same as the fraction of lengths. Rho L over A, if I've got a fraction of L, I've got a fraction of R. Okay, so, the first step I would do, I challenge you here, I throw down my glove at your feet, demand satisfaction. Our physics duel here. First is find the resistance of the wire from hand to hand. You're holding on to the wire, by the way. You were not in series with the wire. You're holding on to the wire. You have not broken the transmission line. Okay, find the resistance of that. You know 200 amperes is flowing through every point of that wire. Can you find the voltage difference from hand to hand? Note that the skin resistance is the same, the path is the same, so I'll just tell you our tote, our skin, our body, my body is 50-50 ohms. Makes you sensey? Did y'all hear the hint? Find the resistance of the piece of wire from hand to hand first, then find the voltage, then find the current. Ready, set, go. If you need me to repeat that, call me over and I'll say it again.
Oh,
What? Someone said Dr. Tucker? Or am I just hearing things again? Okay. Danger, danger. Big danger. Big, big, big danger. Hey, what letter is this? G. Oh, my G. Oh, crumbs. Yeah. If I'm dangling on for my life from a high transmission line, seems a reasonable distance your hands are apart. Hmm. How far is this? Oh, that's 15-ish centimeters, something like that. You're gonna hold like this? Or do your exercises while you're dangling for your life? Half a meter, 50? Whatever, you can calculate with any reasonable number. You're gonna come up with the same conclusion. The danger here is the fall, not the electricity. Spoiler alert. You're way off if you concluded danger. Electrical danger. Oh, you're way on? Right on. What? What? Is this what? Hundred thousand meters. So yeah, good. Wait, 0.15 meters, not 0.15 centi. Did you say 0.15? That's 0.15 meters. Yeah. That's not 0.15 centa. 15 centa is 0.15 m. Yes, I am. Oh, that was loud for the listeners. So if I have 200 amperes flowing through 7 ohms, that means that the total voltage dissipated in that is 1400 volts lost in the wire. Well, resistors don't block current. Resistors regulate, throttle, limit current. You have a big resistor, some current will still flow. How much is the danger? There is no resistance, save infinity, that makes current zero. Nothing. V equals I times R. Unless R is infinity, I is something. I is not zero. Vacuum does not have a resistance. A vacuum is not a conductor. Vacuum is an insulator. Not everything's a resistor. If there's sufficient electric field to rip the electrons off, to ionize one of the atoms in one metal and cause a current of electrons from flowing. The resistance, you do not take a voltage to accelerate, it does not take a voltage difference. If you've got an electron moving, there is a current of that electron motion. It does not take a voltage to keep it moving. What the V equals IR equation tells us is if you've got a material that you've got the electrons moving around in, how much energy, huh? Yeah, inside that material of conductor. Ultimately, you got enough electric field to ionize a single, some metal atoms or whatever. You're providing enough to break the chemical, electrical, electronic bond between electron and atom. That's a threshold. You exceed that threshold electric field force on the electron, then you have started the atom, started the electron moving. You don't need any more voltage. You don't need, give me a threshold problem there. Stick around and ask. The correct answer is no electrical risk whatsoever. Let's do the problem. Let's do the numbers. 15 centimeters over 100 kilometers is 1.5 times 10 to the minus 5 ratio. If I multiply that, 1.5 times 10 to the minus 5, that fraction of the distance times the total resistance of 7 ohms. What's 1.5 times 7? 10.5? Right? Right. So 1.05, oh, for God's sake, it's 1 times 10 to the minus 4, right? Did I goof the 10 to the minuses? I'll take K money's number. I get 10.5, she gets 10.5, 10 to the minus 6, or 1.1 times 10 to the minus 5 ohms. Okay, 1.5, 10 to the minus 5 ohms of wire that you're holding on to times 200 amperes is 200 times 10 to the minus 5. 2 millivolts difference in the wire from this point to this point. All right, your body is 5,000 ohms. 5,000 ohms. 2 millivolts divided by 5,000 ohms is what? 400 microamperes, if I could do that correctly in my head. Did you guys get that? 400 microamperes? Ish. 0.4 millas? 4 times 10 to the minus 4? TLDR, no risk whatsoever. You're at risk from falling from that height. We're done.